In the last number of videos, we've been looking at non-AI versions of data analytics to help us make decisions, decision making when there is uncertainty. And we also looked at distributions like the Poisson distribution. So we're going to take a little bit of a detour here to look at queuing models. And we're covering queuing models here because we want to show the application of distributions. So when you're taking stats and you're looking at all those statistical distributions like normal and Poisson and beta, where do we actually use those? And we want to look at how they inform decision making. Now, in this case, we're not going to randomly generate data from those distributions. Instead, we're using those distributions and we're pulling from that formulas that we can use to make decisions. So we're going to look at queuing models. Now, the idea with a queuing model is that there are often wait times. For example, I pulled this the other day. You can go online to Alberta Health Services and it will show you how long the wait time is at urgent care or emergency rooms. How long is the wait time at a nearby clinic? Okay. If you go and get some blood drawn, how long do you have to sit there and wait for if you're a walk-in? So we want to post wait times. We also post wait times when it comes to services. So if our company provides repairs, how long will it be before we can get to you? Maybe you're the IT department in your company. How long before you can come and fix someone's computer? So it doesn't have to be a business on its own. You could be just within a department within the company. How long before you can get to help the next person within the company, depending on what you're doing. So we want to understand how wait times work and how this relates to those statistical distributions. So queuing models have been around since about the 1900s, and they were first created when there was a common phone line. So the idea here is that we want to reduce congestion and waiting time, and if we were all sharing the same phone line, we want to know how long is the wait until it's my turn. And from an organizational perspective, how many queues or how many phone lines should we have in order to maintain customer satisfaction? So when it comes to a queuing model, we have these operating characteristics. So operating characteristics, and I don't know why this is shifted over. It's been bugging me. Shift it back. All right. Operating characteristics are the performance measures. Okay. You'll probably remember in some of our videos, we talked about receiver operating characteristics, that ROC curve, when we were looking at binary classifiers and false positives and false negatives. Those operating characteristics that originally created that ROC curve were based on when it came to radio transmissions. And how do you measure the performance of a quality radio transmission? And so that was where that ROC curve came into with the false positive and negatives in terms of was information conveyed. Well, here we're not dealing with the ROC curve, but we're dealing with operating characteristics. And in this case, what we're doing is we are looking at performance measures for our queue or our line. So how do we measure if the wait list is appropriate? Well, what is the probability that the system is idle? What's the probability that we have a cashier standing at a cash register helping no one? So there's no one in the queue, the system is idle. We, of course, don't want to pay a bunch of cashiers to stand at a cash register if there's no customers coming through. That's a waste of money. So we don't want to have too many queues, too many lines, that we're paying for all this to run and no one's using it. So we're going to measure the performance of our line based on the probability the system is idle. We also want to look at the average number of units in the queue. So how many customers are standing in line? What's the average number of units in the system? And that would be both those who are being served and those who are waiting in line. So we take how many number of lines do we have? Who's currently being sued? Who's currently being served? So they're being waited on. And then who is in the line waiting? What is the average time spent in the queue? So if you're a customer waiting to check out in the line, how long are you having to wait? What is the average time spent in the system? So that's not just the waiting time, but the waiting plus getting served, that's the part my face is covering up, is the fact that there's time to be helped and there's time where you're waiting to be helped. What is the probability that a unit has to wait for service? So if you show up at the grocery store, what's the probability that you have to wait in line as opposed to directly, immediately checking out? What's the probability that a certain number of units are in the system? So in this case, what's the probability that 5 people are waiting in line? So we can use these different performance measures to assess how many servers we should have and how well the model is doing. A queue assumes a couple things. It assumes a Poisson distribution. So customers arrive in that it is discrete. You aren't a fraction of a customer. You are whole numbers. You are counts. So we're assuming a Poisson distribution for arriving to check out at the grocery store or arriving to the IT department to get your computer fixed. And there is a typical number. So a Poisson distribution here has a typical number within a certain period of time. There is a certain common number. So this here is that in a period of time. So let's say you're the IT department on any particular day, on average, most common, you see 8 people in a day. So within a certain time period, what's the most common count? Okay. So this is customers arriving. The other thing is we assume an exponential distribution for the time that it takes to provide a service. So if we're checking someone out at the cash register, or we're fixing someone's computer, or repairing equipment, whatever we're doing to help out the customer or one of our employees, we assume an exponential distribution. That is, the majority of people don't take a whole lot of time. Okay, so if this is time on the horizontal axes, most people don't take a whole lot of time to check out or to help. There are a small handful of people, this part my face is covering up, there's a small handful of people that they take a long time to check out at the cash register, or whatever problem they have with their computer takes a long amount of time. So we'll assume an exponential distribution, and most units get service in a short amount of time, a small number require a long time. All right, so if we have a single server model, so we only have one checkout location, just one cash register. In our single server model, you wait in line for your one cash register. If we add a second cash register, then we have a separate line for that cash register. So in the single server model, you are paired up, you pick a line, and you then go to that particular cash register. So as we look at these metrics to see how well this model is working, we then need to look at a couple things here. I'm just going to move my face. Not with that. Let's try this again. Move my face. Okay. So in our image here, right, we're showing that these people have lined up for a single server. And we could have multiple servers, but everyone is in their own line for their own server. In that case, what we need to look at is the arrival rate. So what is the average number of arrivals for time period? And then what's the average number of units served per time period? Okay, so we need to have an estimate of the arrival rate and the service rate. If we know these two things, then we can calculate all of these metrics. And so we can start to play with then, what if the arrival rate changes? What if the service rate changes? How does that impact our metrics? And so we talked about the different metrics, the probability the system is idle, the average number of units in the queue, the average number of units in the system, and the average time spent in the queue waiting. What we're going to do is we're going to take these formulas as given. So some of the work has already been done for you. With queuing theory is that these metrics, these are the formulas for the metrics for a single server model. We don't have to impute them or find them from a Poisson distribution. If we know the arrival rate and the service rate, we can calculate all these metrics. which means that in Python, we can create functions for these different formulas, and then we can play with the arrival rate and the service rate to see how well we are meeting the needs of our organization. There are some other metrics here: average time spent in the system, probability that a unit has to wait for service, and probability that a certain number of units are in the system. All right, so let's go look at this in Python. So just a reminder, if you're trying to find these workbooks, we are at drstephpowers.github.io/BIA, and you will find them here under Chapter 10, Prescriptive Analytics. What should the organization do? We are in simulation here. And the first half of this workbook is the Monte Carlo simulations that we saw in the other video. The back half here we're going to do, that's nothing. Back half here is that we are going to do our queuing here. All right, so we are going to import pandas as PD. It's also probably a good idea, if you haven't already done it, to import numpy as NP. It's always good to have those two. Do math and manipulate lists and formatting. It's always good to have those two running. So what we're going to do is we're going to create a function that finds all these formulas here. Make them bigger so you can see them. We're going to take all these formulas, we're going to put it into a function. So we're going to pull probability the system is idle, P0, is 1 minus lambda divided by mu. Lambda being the arrival rate, the average number of arrivals per time period, and the service rate is the average number of units served per time. So lambda divided by mu gives us the probability the system is idle. So we're going to put in this formula into Python so that we can then change lambda and mu and see how this number changes. The average number of units in the queue, okay, so we'll call this L sub q, and it is found by lambda squared divided by mu times mu minus lambda. So we're just going to take these formulas as given. We're not going to derive them. They come from the Poisson distribution and that exponential distribution being combined. That's too much math for for these courses. So we'll just take those and we'll use those for our simulations. Okay, average number of units in the system. So this is being served plus being in the queue. So the average number of units in the queue plus those who are being served. And those who are being served is going to be based on the arrival rate divided by the service rate, because we have the number of people coming in and then how many people can be served at a particular time. That's why we're figuring out how many units are in the system. Okay, average time spent in the queue waiting. So our waiting time is going to be a function of our L sub q, the average number of units in the queue, divided by lambda. So if you're in the queue divided by the arrival rate, that's going to give you the average time spent. 3 more, average time spent in the system waiting plus getting served is then going to be this average time spent in the queue waiting plus 1 divided by mu, which gives us the time for being served. Okay, so then here is the probability that a unit had to wait for service. So here's the probability of waiting. Lambda divided by mu gives us that. And the probability that a certain number of units are in the system is going to be this P0, which you remember is the probability the system is idle, too far, times lambda divided by mu, which, remember, lambda divided by mu is the probability that you have to wait for service to the power of n, right, where in our n, we're looking at the number of units in the system. So if this is the probability that you have to wait for service, what's the probability? 5 people are in the system. We take the probability that you have to wait for service times, repeat that 5 times, times the probability that there's nobody in the queue. Okay, so in Python, what do we do? All right, once we have gone into our simulation, we have opened in Google Colab, we have logged into Google Drive, we have saved a copy for ourselves. We can then manipulate this data set here. With NumPy and Pandas, we are creating a function, and that's going to be a function of lambda and mu. Okay, so I'm just going to call it lamb for short. And I put in my formulas here. So this is where we go back to our Python coding video where we talk about how to do basic math in Python. And so that first one, the probability that there's nobody in the queue, was 1 minus lambda divided by mu. Okay, L sub q was, if we go back to the formula here, and I'll make it big so we can see it, we have lambda squared. To do lambda squared, there's a couple ways to do it. Here we're going to do the power. Lambda comma 2 says it's lambda to the power of 2. And then we're going to divide that by mu times mu minus lambda. So parentheses matter to make sure we're doing it in the right order. And again, we are using those math functions that we learned earlier. I don't think we did power here. So we use another method, which is the double star to get the lambda squared. You could do that instead. Lambda star star 2 to replace that here. You could do that approach as well. So there are a couple different methods. All right, so here we have our formulas. Our function, we're going to give it a lambda, give it a mu, and it's going to output these different metrics. So we're going to run that. So what we want to do is we want to find the probability. We're going to define single serve probability as a function of lambda mu, and we're going to give it an n. So this is to do that very last one. Let's zoom in here. Okay, this very last question. Probability that a certain number of units are in the system. Well, let's have it do a number of different units in the system and give us the probabilities. So what's the probability that one person is waiting at the grocery store? 2 people, 3 people, 4 people. And so with this particular one here, because it's different values of n, we can then, in our Python code, we can make this here a loop where we populate our empty list and we put all of that into a function where we give it lambda and mu and an n, and then it loops through the different amounts of n to find out the probability that there are n number of people in the system, and it'll output that list. So we're going to create an empty list, do a loop where we keep calculating that last metric, and then append it by adding the I, which is whatever scenarios of n we have, and then the corresponding probability. And we'll put it into a table because we like to see things in tables. What is the probability and what is the number n? So we're going to create these 2 functions. Now that we've created these 2 functions, let's do some testing here, some simulations. So let's suppose that lambda is 0.6 and mu is 0.9. So just to go back, lambda, got to figure out how to make this bigger. Lambda is 0.6. The average number of arrivals per time period. Okay. The service rate is the average number of units per time period. So how come these are fractions? Well, maybe the time period is per minute. So if our time period is per minute, then we don't have we don't have 2 people arriving every minute. We have people arriving every other minute. And so our lambda and mu can be percentages depending on what time period we are using here. So perhaps that every minute it's 0.6 is the number of people arriving. That's to represent the fact that they arrive more than a minute apart. And then mu, right? Mu is our average number of units served per time period. And so we're not able to serve 1 person every minute as our list here, but pretty close. So let's say we're able to check out about 1 person a minute, but people don't arrive at that speed. And then we can look at what is the probability there are 0 people waiting, that there's one person in the system, 2 people, 3 people, 4 people, 5 people. So we set out our values, then we call our single serve model here with our lamb and mu we have just provided. And then remember that this function outputs p sub 0, l sub q, l, w sub q, w, p sub w. So you want to make sure that when it outputs it, you give them the same names, because otherwise it's just giving a list of numbers. And you want to make sure you know which one in the list is which. So you copy this directly here, this return, copy this to match and put it right here so that when you output it, you get the same ones matching the same spots. And I could take this output then and I could have it be so that it's going to say for the single mod, so it's going to give me a report. And I'm going to use a dictionary. So variable probability idle is the p underscore 0. The average units in the queue, L underscore Q. Average unit system is the L. Average time in the queue, WQ. Average time in the system, W. Probability we're waiting, P sub W. So if I create that dictionary, then I can give it values of lambda and mu, and I can call that function, and then I can have it give me a report. So based on this scenario here, where our lambda is 0.6, so the average number of arrivals per time period is 0.6, and where the service rate, the average number of units served per time period, is 0.9, and we're checking these different numbers of people in the queue, the probability we're idle is 33%. The average number of units in the queue, so that's going to be waiting, is 1.33. Average units in the system is going to be 1.99, so we got people being helped plus people in the queue. And our average time in the queue, 2.22. This is going to be in that same measurement that we're setting lambda and mu. So here the average time waiting is 2.22 minutes. The average time in the system is 3.33. And remember, the average time being helped is just less than 1 minute. So that's why this queue plus system, you notice, is about a minute apart. The probability you're going to have to wait, 67% in our single server model here. To get the probability for a different number of people in the system, we can call the other function we created, which is single serve prob. It had 3 parts, lambda, mu, and n. We define lambda and m and mu, further above, so we don't have to rewrite them out. We simply need to call it and produce this here. And so what we see here is that the probability there's 0 people in the system here is a third. And let's just go back. Is it in the system or is it in the queue? It is probability that they're in the system. Okay. So probability there's 1 person in the system, 22. Probability there's 5 people in the system, less than 5%. So we can see here the probability of different number of people, and that's really going to come down to how quickly they arrive versus how quickly they get serviced. Okay. Now we could try different values of lambda and mu. Those are going to be based on how you measure the time. So if we have, in this case, where we have, let's change this. What if they're the same? What if we have lambda 0.9 and mu 0.9? Average number of arrivals per time period, average number of units per time period. So if the rate at which people are coming and the rate at which we're servicing are the same, notice how it conks out. And that's because the way the queuing model works is that you have to have, when it comes to this ratio of lambda and mu, you can't have an infinite queue. So as lambda gets to be the same size as mu or bigger, then there's more people coming in than can be serviced, and then your queue is of infinite size. It just keeps getting bigger and bigger. You're not able to reduce the size of the wait list, So your lambda, in order to use these methods, in order to actually have a queue that you can keep track of and not one that just gets bigger and bigger for infinity, lambda has to be smaller than mu. With lambda smaller than mu, we can run this. Notice that lambda got bigger than we had before in our original scenario. And so now the probability that the system is idle is lower, and the average time in the queue is now almost 9 minutes. The average time in the total system is 10 minutes because there's the 1 minute to be serviced essentially. And so we can see as you change lambda relative to mu, what that does to the wait time and the number of people who are waiting. Okay, so you can play with that lambda and mu. So again, I'm just going to show this for the billionth time. Arrival rate, that's lambda, the average number of arrivals per time period, and the service rate is mu, the average number of units served per time. We are using fractions because we're measuring it in minutes, because we want the wait time here, this average time in the queue and average time in the system, to be in minutes. Okay, so just keep that in mind as you're trying to figure out what is lambda and mu. You change it to months, then you're changing the other measurements to months. Okay, all right. Let's stop this video here. In other videos, we'll look at other scenarios, like what if we have a multiple server model. So this was a single server model. You've gotten a line for a particular checkout. More and more, if you think about Walmart, Canadian Tire, they are moving to a multiple server model, one long line, and then you move to whichever checkout clerk is available. So we'll look in our next video at the multiple server model.